Hello everyone. Today we are going to continue talking about message passing interface. Last time I mentioned that message passing interface, or MPI for short, has several steps that you need to add to your program. Our default programming language here is C. However, note that libraries for MPI is available in other programming languages such as Java, Python, and others. So in C and similarly in other languages, we start with an include file. So you have to include the library. That is typical. I'm sure you are familiar with it. Then we have to initialize the MPI program, basically the initialization step. That is just one command that you have to pretty much copy it. So there's nothing specific about that. However, we are going to explain it in the next slides. And then the main part of your program will be performed, which is the communication and the algorithmic part of your code. And then eventually, once you are done with all the parallel parts of your code, you just terminate MPI. So now let's go deeper on each one of these steps. I guess this one I explained. The only point that I should mention here is that using the library, let me use the pen here. So MPI.h must be included in the beginning of your program. I guess all of you are familiar with it. Otherwise, all other MPI commands have this general format. So MPI, let's say something, and then it will give you an output which is generally used for error catching. So I'm sure you are familiar with that. So let's start with an example, because you are familiar with programming, and just we can dive into the two examples and learn by examples. So here I want you to map this slide with the slide that I had with the one that we had a couple of minutes ago. So as you can see, in conformance with that slide, in the beginning we have a include part. That is the easy part. And then the rest of it is just a C program. So the good thing about MPI is that you do not need to learn a new programming language. So it's just part of C, and you can see that everything is like C programming. Nothing is new except the MPI parts. So then, before you do any MPI operations, you must add this MPI init, which stands for initialization, in your program. And then you know that in C, the program receives two arguments, known as argc and argv. So you just have to pass them exactly like what you can see here to this MPI init program. So this line, this initialization line, can be pretty much copied and be used in any MPI program. So this is no-brainer. And then this is the main logic of your program that definitely varies from one application to another. And then eventually, when we are done, we need to do the MPI finalize to terminate the MPI and move on. We can move on with our normal program, but we cannot use any MPI after MPI finalize. All right. So I guess I talked about this. Now let's make our example one step more realistic. We want to just do a hello world program using MPI. In this program, all the parallel processes, you know that we are doing parallel processing, so we have multiple processes that are running on different machines or on different cores of the same machines. So of the same machine. So it does not have to be on different machines. That's what I'm trying to say. However, generally it is used in that configuration, which means across several machines. All right. So again, we have MPI.h. That's the easy part. Then we have the main part. That is also you are familiar with. That's a C thing. Then we have a couple of variables defined that you That's not a difficult thing, but you can see them often in many MPI programs known as number of tasks and rank. I will explain them one by one. And then we have MPI init that I said it can be copied. It's like a easy one, like just MPI init argc argv. You just pass parameters and just initialization. We don't care about what is happening behind the scene. It's pretty much configuring the MPI. There's just one thing I want to talk about it that I will talk in the next slide, but I briefly mention here that one of the things that this init command does is creating a network. Of course, I mean an overlay network, a software network, not a physical network. The physical network, our assumption is that it is already in place. So we are talking about the software network between the processes that want to talk to each other. So that is known as communicator. We will talk about it again. However, I want to tell you a communicator is like a software-defined network. It's not a real network, but just a network between processes that want to communicate with each other. So MPI provides us, or MPI init provides us with one default communication network, or it's known as MPI com world, as you can see here. MPI com world, you see it very often in the MPI, and that is the default networking or communicator it's called in MPI. So basically, when you say MPI com world, it means that all of your processes can communicate with each other. Yes, you can make restrictions. A subsection or a subset of your processes can just talk to each other. That's for more advanced MPI programming. In this part, we just do the introductory. The goal is just to make you familiar with MPI programming. Other than that, MPI by itself can be a topic of a course on parallel programming, and the whole semester can be spent on that. There are more than 150-ish MPI commands. Each one has its own complications, and we have MPI, we have parallel algorithms that has its own difficulties. But here our goal is not going that deep. Here the goal is just making you familiar with the basics of MPI. All right, so here we can see two MPI commands, MPI com size, the first command, and MPI com rank. Well, the size is a very easy command of MPI. It just tells you the size of the set of processes that are going to talk to each other. Let's say if there are 3 processes or 4 processes, assuming that you have 4 computers talking to each other in your distributed system, so the size would be 4. If you have 16 computers, it would be 16. So what this MPI command does is just build the communicator network. I mean, it doesn't build it, it uses the com word, and then the function figures out the number of tasks or the number of processes, and then put it in number of task variable. Remember that number of tasks, we have already defined it in our program. Okay, the other instruction, the other MPI command is even more important, rank. So you must remember from socket programming that we have IP address and port number, and together they were forming socket address, and we were using that as a communication vehicle between processes when we were doing socket programming. That was a little bit difficult. Here, MPI has made this communication very abstract for us. We do not deal with IP addresses. We do not deal with sockets. We do not deal with port numbers. All of those things exist. They are managed behind the scene. What we work with is just the rank. Each process in MPI is get a rank, which is just an integer number, like 1, like 2, very simple numbers. It's just a number that is assigned to each process, and then using that number, the processes can talk to each other. So that rank is known as rank in this literature. Using that rank, all the processes can talk to each other. Each process has a rank, replacing all those difficulties of IP and port and socket and all these. We just have a rank for each process. All right. So what MPI comp rank does is basically assigning a rank to the program that is running this code. And do not forget that this piece of code is running by all participating processors, all participating machines. So let's say if you have 4 machines in your cluster, all 4 machines run this command, run this code. And therefore, all of them run this command, MPI com rank. Therefore, all of them are assigned a rank, a number. All right. And then all of them reach to this line, which is just a printf. Let's say what will it print? Hello world from process. This is just a text. It will be printed as it is. Percentage %d and percentage %d. So one is rank and one is number of tasks. So the output of this program would be hello world from process 0 of, let's say, 4. Process 1 of 4, process 3 of 4, process 2 of 4. The order does not may not be preserved. So basically, first one might be number 3, second one might be number 4, whatever. So the order is not guaranteed to be 0, 1, 2, 3, whatever. It can be any combination of those things. All right, and eventually we have MPI finalized that you are familiar with. Okay, I guess I talked about these things, so let's move on to the next slide, telling you how to compile and run your MPI program. There are different compilers for MPI. One of them is MPI CC. The other one is MPI CH. There are many variations of it that you can install and make use of. All right. So first you have to compile your program. As you can see here in the command line, you do MPI CC. And then the name of the source code .c, and then -o, which tells that we are going to create an object file, and then the name of your object file, which in this case is hello world. And then once it is created, once the object file is created, you can run it using MPI run. And then this is the object file, you are familiar with it. And then NP, number of processors. NP stands for number of processes. So here you want it to be run on 3 processes. And then the last parameter here is the list of machines that that constructs your network. So that can be built automatically or can be read from a text file. All right. So here, basically, you provided with a list of machines. All right. So let's say the example running of it would be MPI run on 3 processors, and then this is the text file that includes the list of the machines that you have, and then here is your object file. So you have to give it the list of the machines. And then here is the output. Hello world from process 0, hello world from process 1, and hello world from process 2. All right. And then still you can run your program as if the MPI part doesn't exist. And that's the beauty of MPI, that you can run your program within MPI like what we have done here in the parallel mode, but the same object file can be run to use in an ordinary way, in a sequential way. So basically in this way, if you run it, all the MPI parts are ignored, and then you just get one output, hello world from process 0 of 1. In other words, just one core has been used, which means a sequential source code. All right, in the next set of slides, I will continue teaching about MPI with more details.